I should take a moment, however, let's do that, to figure out how to pronounce this word. Fortunately, Merriam-Webster has an online dictionary, and according to this, let me turn the volume way up. According to this, we can hear how it's pronounced.
Periodicity.
Okay, periodicity. Well, that's not hard. This is the one I have been waiting for, when we would get to talk about modeling. For me, that's not the only thing, but that's the primary thing for the value of mathematics. Is now we've gotten through some of the technical stuff, we can apply it. How is it useful? If it can model some real-world phenomena, it's very useful. And a lot of real-world phenomena are sinusoidal. We'll take a look at that. Suppose you had a sinusoidal curve, which we do, don't we? These are the points we're talking about here. Oh, it's also drawn down here. Find the sinusoid that fits this data. Mr. Schwartz suggests that this problem is easier if we choose cosine, and perhaps it is, but oh, just to be different, I thought, let's try sine. And it seems to me that sine looks pretty appropriate here because don't we have it's starting around the central axis? Yeah, I think sine would be the one to do. It's not reflected. It starts by going up, so we're going to have a positive A. Our central axis is right here at y equals 3. So we have a D equal to 3. The height above the curve, above the central axis, 3 to 5 is 2. So we've got A is equal to 2. The period here goes from 1 over 2, 13. So what's that distance? 12. 12 radians. The period of a sine wave is 2 pi, and we know that the period of a function will be 2 pi divided by the frequency of cycling. We want to know b, that's what we put into our equation. So we just divide 2 pi by the period, which we observe is 12, and we get a b of pi over 6. So what do we end up with? Y equals 3, that's our vertical transition right here, plus 2, that's our amplitude, and it's normal, it's not reflected, so it's positive 2. Sine, we put our frequency in here as a multiplier on our angle variable minus whatever we have for phase shift. I didn't talk about the phase shift, but in a parent graph it would start right here at 0. This has been shifted to the right 1 unit, so the phase shift is 1. Now this should be checked with a calculator, and when you do, you will see a curve that looks just like this. Let's try another one. Find a sinusoidal curve that passes through these points. Okay, I'm just going to look at how x relates to, all these x's relate. This is 3 plus 4 is 7, plus 4 is 11, plus 4 is 15, plus 4 is 19. So, nice. Yeah, they're equidistant. My first point, y, is at 5, and my next one is at -1, and my next one is at 5, and my next one is at 11, and my next one is at 5. Now these look to me like they match up pretty well to what we would expect to see for our 5 critical points, right? Our 5 key points. And when we put them together, a sinusoid. And which one would you choose? Would you choose cosine or would you choose sine? I agree with you because we're starting really at the central angle. So it'll be sine, y equals sine of x, but it isn't normal. It is reflected. So my a is less than 0. It's going to be a negative. Well, let's determine what d is. It's right here, isn't it? At y equals 5. That's these points right here. So d is 5, so we have a vertical translation up of 5. And our a is going to be negative something. What is the amplitude? Well, from 5 to -1 is 6. From 5 to 11 is 6. Our amplitude is 6. Do we have, what do we have for a frequency here? Well, we're working with sine, so we're 2 pi. And what do we see is the full cycle, the length of one full period here? It's going from 3 to 19, so that's 16. We're pi over 8 for our b. And is there a phase shift? Well, there surely is. It's a positive 3. So let's put this all together. I'll say y equals whatever my vertical shift is. Okay, there is one of 5. And then minus 6 times, well, I don't need to put that in parentheses. I will need parentheses in a minute. Well, let's wait till I really need it. Sine. Now I need the parentheses. We've got that as our frequency, and our angle measure x minus a positive phase shift looks like this. Now let's verify this one on our calculator. You know from working with me in the past that actually is pretty important to do this kind of verification. First of all, I want to make sure that I am in radian, which I am. Let's put our window together. I'm going to set y min at 0, not because I need that to see the full curve, but just because I want to make sure that we see that phase shift. My x max I'm going to set to 19. 19. And let's put the scale at 4. My y min will be -1. My y max will be 11. And we'll use a y scale of 1. Let's put our equation in. My vertical translation 5, it's reflected, so I'm going to say minus. My amplitude is 6. I'm using the sine wave. I've got a frequency of pi divided by 8, which multiplies times the variable angle minus the phase shift, a positive phase shift of 3. Let's graph it. Looks very good, doesn't it? So that would be a place I would pick up an error if I had made it. Modeling with sine and cosine functions. The voltage in a household outlet can be modeled by this equation right here. We usually refer to that household voltage as being 210, don't we? Oh, no. That's this one down here. Or 220. This one. Electric ranges that use the higher. But for the one we usually use, it's 110 or 120 volts, right? That's the one that, oh, let's see if I can do it right, with the grounding pin down here, right? And you plug your laptop or your computer into that, right? But electric ranges and ovens, they often use higher voltage. We're going to try graphing this one. I'm going to use the window that's described here. I haven't been doing it this way, although the Roxwold book does put the description of your window together this way. This is X min, X max, X scale, and these are the Y's. So let's go here. We're going to be sticking with radians, but I want to make an adjustment to the window. I'm going to start with 0, so that's good. But my Y max is going to be 1 divided by 15. My Y scale is 1 divided by 60. Yes, you notice that turns everything into decimal. Y min is going to be negative 400. Now we know it doesn't actually need to go to negative 400 because what do we see here for our amplitude? 310. Oh, it didn't like that. Okay. Let's go back to the window. You know what it didn't like. I should have used this negative. If you use the subtraction, the operation negative, it will kick you out, as it did me. 400 and 100. So we're ready. Now let's put our equation in. Our voltage in terms of T, we're going to use Y and X when we put this in. Let me clear this. This will be 310 sine 120 pi times X. And let's graph that, see what it looks like. Looks pretty good. It actually does have an amplitude of 310, as we would expect. How do we describe this voltage? Well, it's varying from positive 310 to negative 310, and in the course of 1/15 of a second, it varies 1, 2, 3, 4 full cycles. Okay. Evaluate the voltage at 1/120th of a second. Okay, let's try that. I'm going to clear this and we'll put in 310 times sine. I'm going to use this right here. 120 pi times 1 divided by 120. Put in the second parentheses. So this should give me what the value of this function is when t is equal to 1/120, equal to 0. Let's look at our graph. If this whole thing is one 15th of a second, and I'm cycling 4 times. This is at, actually we can't even see our little tick marks, can we? This is at 1/60th of a second, then 1/120th of a second would be right here, and indeed it is 0. Approximate the root mean square voltage. Okay. Let's try $3.10 divided by square root of 2. That would be the root mean square, wouldn't it? Pretty close to 220. All right, we've gone through it. This is just what we did a moment ago. I had worked this out in advance. That's what we saw when we put that in. We described the voltage in the circuit as, well, I'm not sure I used the word sinusoidal. I should have. Varying between -310 and +310. We evaluated 120. We actually didn't talk about what the result meant. We didn't interpret it. Unless we say, well, halfway through the cycle, the voltage is 0. I guess we could have said that. And approximate the root mean square voltage. Boy, I hope this is, yes, it is. So the 220 that you have in your house for your heavy-duty circuits, this is describing what's happening with the electricity. Some of you may go into electrical engineering. We find that very interesting. If a projectile is fired with an initial velocity of, I'm going to mark this with v feet per second at an angle of that, it will follow a parabolic path described by v squared and the cosine of the angle squared. These are in the denominator. Here's the variable. That's the angle varying. This angle here, the angle at which the projectile is fired, that is not varying. What's varying is this, right along here. So those parts that I just marked, those are not varying. Those are going to be 7, I'll mark them here too, they're going to be 750 and 30 degrees. Those are fixed. Let's put the equation into our calculator. We're going to say, turn on the calculator is what we're going to say. Oh, I would be in the wrong mode now, wouldn't I? We want to be in degree mode for this one. Enter. Okay, degree mode. And my window, I'm going to match it to what we've got here. I've got x min, okay, we'll go from here to here, x min of 0, x max of 20,000, x scale, there's 12, I already counted them, so that would be 20,000 divided by 12 is my x scale. I'm trying to match what I've got in front of you. My y min is 0, my y max is 2500, and my y scale is 2500 divided by 12 again. Okay, so now let's put in our equation. See if I can do it properly. We have a negative 16x squared divided by, and I better put parentheses around this, v squared, and that's 750 squared times, I think I'll use parentheses again, cosine of 30 degrees, and we're going to square that, and that's all of my denominator, plus, and I'm going to use my variable again. I've used it once squared, now I'm going to use it as a linear. This is a quadratic, isn't it? When you've got x squared, it's a parabola. And of course, we know it's going to open downward because this is negative. Oh my goodness, this is great. Tangent of 30 degrees. Okay, now let's graph that and see what it looks like. Yes. Okay, so let's see if I can trace this. This is so hard to read here. Trace. Okay, with trace, you can look at the point values. And one of the things you're going to see here, this is about the maximum, isn't it? Let's 2196, 2197. Okay, so 2197 is maybe the max. And where am I with x when that occurs? See over here, it asks you to determine the coordinates when maximum height occurs. We just used our trace function to approximate that. Assuming the ground is flat, by reading your graph, find the total distance traveled by the projectile. Okay, for that, I'm going to keep my trace alive here. And you notice that x is getting larger and larger and larger. Actually, we expect it to be twice what it was at the max, because what do we know about parabolas? Yes, they're symmetrical. Okay, so about almost 1500, approximately 1500. Now, I had figured these out mathematically earlier in my life, and that looked just about what we had and just about what we estimated by reading the graph right off our calculator with the trace function. Here's what I've been waiting for. This is so good. I actually took data back in 2007 right off of Live Earth for Portsmouth, New Hampshire. What I was interested in was what was the average high month by month. And I'm going to consider these months to be 1, 2, 3, 4, and so forth from my calculator, because we're going to want to see whether or not we can fit a sinusoidal curve to this. I love using real data that belongs to us, and for most of us, Portsmouth is part of our lives, isn't it? So how are we going to do this? You're not going to do a whole lot of this in the first semester, but in the second semester you will do a lot with statistics. So we're going to do a little statistical process now. This is learning how to use your calculator well. I'm pretty excited about this. So turn your calculator on and let's go to Y and clear that out of there. We're going to want to be in radians. You'll see why in a minute. Oops, wrong thing. Mode. Okay, so we want to be in radians. Now, you're probably thinking, why is she saying that when we're looking at degrees? I understand the question, but these are not measuring angles, are they? And as a matter of fact, this is going to be the output. This is going to be the Y. This is a temperature. These are going to be our input, and these are going to be just plain numbers. So we want to be in radian mode. Okay, and now we're going to go to stat plot. We're going to turn a plot on, enter, and then turn it on, enter. It's going to be a scatter plot. We will need an X list. That's our independent variable. That's going to be our time. We're going to do our months. And our dependent variable, which is going to be Y, that's going to be temperature. Okay? So we're going to do our first statistical work. We're going to set up a scatter plot. So you go to Stat, Edit, Enter. We're going to start with the first list. It's going to be simple to put in. 1, 2, 3, 4, 5. Okay, let's do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is easy. 11. Whoops. If you hit the enter button, it's easy. 12. Okay, so I have all my time values in here, just naming each of the months. So 1 month has gone by, 2 months, 3 months, etc. Now we're going to do L2. This one, I just have to make sure I put the numbers in correctly. 3, 4, 3, 7. You should be doing this right along with me. 4, 6, 5, 6, 6, 8, 7, 7. In fact, if you don't do it right along with me, you're just about bored out of your squash right now. 83, 80, 72, 61. I hope I'm staying right here. 50, 39, enter. Okay, I have all my data in. Now, let's see what it looks like. We're going to plot it. Zoom, the zoom function, will let us plot in a number of different ways, or set our window in a number of different ways. I want to make sure the window will include everything I'm interested in here. So I'm going to do zoom stat. It will look at the statistical information we put in the list. That looks rather like a sinusoidal curve, doesn't it? Is there a pattern here to suggest a model? I'm going to say that I think there is. Okay, so let's put this aside for a moment, and we'll think about what that model would be. I'm going to clear away those. Okay, suppose we select sine as a model. You might have wanted to select cosine as well, but I'm going to select sine. In order to figure out where the central axis is, I'm going to look at the minimum value and the maximum value and find what would be midway between. Okay? My minimum value occurs in January, it's 34. My maximum value occurs in July at 83. So I add those together, divide them in half, and I have the central angle, the central axis for this model. Calculate the difference between the minimum and the maximum, and then divide by 2 to find the amplitude. Makes sense, doesn't it? For here, we wanted to find the midpoint. For this one, we want to find the distance from the midpoint to the peak. From the valley to the peak gives us a distance twice as long as what we are interested in. So we find the total distance from the valley to the peak, divide it in half, and we have our amplitude. Now we have to consider what is the frequency here. We're going to divide 2 pi, the full rotation for sine, by 12, the full cycle for seasons, and we'll get our frequency factor. You can already tell me what it is, can't you? That's right, pi over 6. The question coming up next is a phase shift necessary here? Well, we'd expect this to start cycling, the beginning of the cycle, to occur right at the midpoint at 58.5. So let's see. The closest we have to 58.5, here it's rising, that's what we want, the temperature's rising, is April, the 4th month. So we're going to say that our sine wave has to be moved in positive direction 4 months. Okay, so we're going to shift the cycle from 0 to 4. Now let's go back after we've done all of this and take a look at how our data plots. Turn this on and see if this is all making sense. Well, it's hard to make much sense out of this because I don't show a window. I don't show any tick marks. This window, by the way, it calculated itself, and it's got really weird numbers on it. Zoom 9 will display it for me again. Okay, I'm going to put that aside for a moment. We'll go to the next page. We're going to take this information that we just put together. Vertical shift of 58.5, amplitude of 24.5 with a normal shape going up and then down, a frequency of pi over 6, and a phase shift of 4. Woof. There's a lot to think about here. We are going to use our A, our B, our C, and our D. Now, on this one, I'm showing that adding the D at the end. I could have had it at the beginning. The mode we're in is radian. Now we're going to try that. Let's see. 25.4. We're going to try this function and see how it graphs. This is going to be pi divided by 6 is my frequency. And then we've got x. We're going to subtract our phase shift, which is a positive 4. And we're not going to forget our vertical translation. Actually, I like it when I put it in first. Okay, let's see if this makes sense. 25.4 sine, and there's my frequency. There's my angle with its phase shift, close parentheses, close parentheses. I think that's good. Let's try graphing that. Wow! How well does it fit the data? Almost perfectly. You know, this is just data we took on average temperature. So see how these sinusoidals describe things that happen around us? This is definitely an acceptable model. Wow! Oh, I couldn't be happier. Okay. Wow, that works so good. Okay, homework number 4, back in class.